So continuing our work in Unit 4 over work, power, and energy, now we're going to focus a little bit more on the power aspect of it. So the quantity of work done is a force over a displacement. Work has nothing to do with time. So if you do the same, and this is usually sometimes students' argument for why they take so long to do their work, it doesn't matter how long you take, you're doing the same amount of work. If you do work very quickly, it takes the same amount of work to do it very slowly. Although, that's not true in homework usually. Instead, that might work only in physics. So what do we do with the time aspect? Well, that's where power comes in. Power is the rate at which work is done. So you want more power, get more done in a short amount of time. The SI unit of power is the watt. And for historical purposes, the horsepower was always kind of used to describe power of a machine. And so it was actually used to describe 1 horse. Power is equivalent at lifting a certain 750 Newton object 1 meter per second.
What is that in like kilograms or pounds?
750, well, you divide that by 10, you got 75 kilograms. The W in the power equation is work, or the WE. Work over time is your power. So as you have this wonderful, awesome tracksuit walking up the stairs or running up the stairs, because again, you're looking at the amount of work needed to go up the stair. By doing that amount of work faster, i.e. running, the difference will be the power output. Basic values of power in watts. The car moving at 40 miles an hour has quite the power output. A stove, sunlight from 1 square meter. Refrigerator. Walking up the stairs, 150 watts. Your brain just surviving only takes 20. So let's try a couple problems out. To pass a slow-moving truck, you want your car to accelerate from 13.4 meters per second to 17.9 meters per second in 3 seconds. What is the minimum power required for this pass? Now, when we look at our power equation, the only thing that we see is that I have the work. I don't have work, I don't have power, and I don't have time. So that means we should probably start looking at, okay, work is equal to force times distance times cosine, but since it's on a flat, that's going to kind of cancel that out, right? but we also have our understanding that Verk is equal to the change in kinetic energy. Do I have enough for kinetic energy? Which one's going to be probably the easier one to solve for? Verk, which then I need to find a force, right? Which is an acceleration. Or could I solve for using the change in kinetic energy, which would be the one half mass times velocity squared, and we could say final minus the initial. And we would be able to find the amount of work done as well. So we have some options here. I'm going to go with the change in kinetic energy route. So I'm going to resize this here. Let's go with the final, calculate the final kinetic energy. So that would be mass, so 1.3 times 10 to the third kilograms times the final velocity squared. So from there, I would do, after doing that calculation, I have 208,266.5 joules, and not the bling bling kind. Continuing right along, we will calculate then the initial energy. So 1/2 times the mass times the velocity, initial velocity squared. Putting that into my calculator. That should give me an answer of 116,714 joules. Now I need to subtract those two from it. So it'd be 208,266.5 minus the initial, and I get a change in energy, or Verk. So it is Verk, or change in kinetic energy, of the 91,552.5 joules. I can then take that and divide it by my time, which is 3 seconds. To give me an answer of, this would be 30,517.5 watts, or 30.52 kilowatts. So we have some things that are going to help us out. The fact that we have a force helps. We do have an angle, might help. We have a mass, may or not help. We do have a power. Okay, being as that this is a power problem, we at least should, again, pay attention and say, okay, power is equal to work divided by time. Now, again, because I don't have work, that is equal to a force times distance times the cosine of theta. I don't have any velocities because I'm asked to actually find out what is the maximum speed of the car, so velocity is probably what I'm going to be looking for. So I can't use the connection between work and kinetic energy in this problem. However, if I resize this here, I'll be able to utilize a little bit of space here. And if I do a couple substitutions, if I say that power is equal to work divided by time, and work is equal to force times distance, I can then say that force times distance times the cosine of theta divided by time is essentially also the power equation. Now, if we look carefully, we might notice something. And this is usually where a lot of things go wrong. I have a distance divided by time. What's that the equation for? Velocity. And therefore, I have a force, I have a degree. I just need to get rid of it on that side, don't I? And by doing that, I will be saying that all of that is equal to distance divided by time, which is essentially velocity. And it's that little, recognize that is what some problems go, oh, and they are slightly frustration. So if we substitute things in, as we should, and well, we do have it in 50 horsepower, so we should probably convert that into watts. If I'm not mistaken, 1 horsepower is equal to 746 watts.
Power equals 746 watts. Okay.
So now that we have that canceled out, so 50 times 746 gives me a wattage. Let's get rid of that color. I don't like that color, especially in the middle of a problem. Let's go blue. 387,300 is equal to a force of 1,280 newtons times the distance times the cosine of 5 degrees divided by the time. We can do some math. Either we can multiply the 1,280 times the cosine of 5 degrees and just kind of get one number, or we divide both sides by that same quantity. I don't think the math should work out that it literally does not matter. That order, that I can actually have it set up such as that. Divide that by, or my number by the quantity. Make sure we use parentheses in the proper way, otherwise, yeah, you would have to do it as it is. And we get 29.3 meters per second.